Imagine trying to lay down over 1,000 kilometers of heavy steel track. We're talking tracks meant to carry massive passenger and freight trains. But here's the catch. Your foundation isn't solid rock. It's not even stable dirt. Your foundation is ground that literally melts, shifts, and completely collapses under the heat of the sun. It's kind of like trying to build a massive skyscraper on a giant mattress of melting ice cream. So how on earth do you build a massive railway on ground that is constantly melting? Welcome to The Explainer. Today, we're unpacking one of the most mind-bending engineering challenges on the planet. And honestly, the solutions they came up with, they might end up saving infrastructure right in your own backyard someday. We're going to explore how massive economic demands are practically forcing human ingenuity to conquer the most extreme terrains on Earth, culminating in what I think is absolutely one of the greatest technical achievements of our time. Okay, let's look at our roadmap for today. 1. Global growth demands infrastructure. 2. Conquering extreme terrain. 3. The permafrost railway challenge. 4. Crushed stone embankments. 5. Heat pipe systems. And finally, 6. Securing long-term stability. Let's dive right into Section 1, Global Growth Demands Infrastructure. Just think about this number for a second. $83.57 billion. That represents India's record-high foreign direct investment for a single year. And man, that kind of money acts as an unstoppable force. I mean, $83 billion doesn't just sit around in a bank account gathering dust. It builds steel, it pours concrete, it lays rail. It absolutely demands massive, sprawling logistical infrastructure to move goods, services, and people around. And notice how actively governments are accelerating this whole thing. When you lift limits, like, say, allowing 100% foreign investment in telecommunications or jumping from 26 up to 74% in defense, explosive growth is going to follow. It just happens. But all that new business, it needs to physically exist somewhere. And because the easy, flat, stable building sites around the world have pretty much all been taken, these booming economies are now forced to punch their way through literally the most extreme, unforgiving terrains on Earth. Which brings us to Section 2. Conquering extreme terrain. Take the Atal Tunnel up in the Himalayas, built at these crazy altitudes where oxygen is scarce and temperatures just plummet to -30°C. To pull this off, they used the new Austrian tunneling method. So instead of just blasting a static hole and, hoping for the best, engineers actually treat the mountain like a living, breathing adversary. The mountain is actively fighting back with 1.9 kilometers of pressure. So the engineers literally have to listen to the rock. They're continuously monitoring deformation, dynamically adjusting their use of shotcrete and rock bolts. They're basically leveraging the rock's own shifting weight to support itself. It's brilliant. But, chemical innovations are just as critical as the physical digging. Deep inside the Gotthard Base Tunnel in the Alps, workers were facing 40 degrees Celsius heat and transport distances of up to 30 kilometers. If you've ever poured a driveway, you know concrete is basically a ticking time bomb. Imagine needing it to stay perfectly liquid for a massive 8-hour road trip inside an oven-hot mountain. Well, they solved this with Sika ViscoFlow. It's this slump retention polymer that extended concrete workability to an amazing 8 hours, completely changing the game for what was possible underground. Or, hey, consider the Millau Viaduct over in France. By stepping away from traditional concrete and using this highly advanced, super thin, weldable steel called DIMC 460 TMC, engineers achieved an absolutely incredible 82% weight reduction. Now, why does that matter? Well, because overcoming the brutal gravity and fierce winds in those massive valleys was physically impossible before this specific steel alloy came along. It literally changed the math of bridge building. All right, let's move on to Section 3. The Permafrost Railway Challenge. Stretching 1,142 kilometers, the Qinghai-Tibet Railway connects central China to Tibet. But here is the kicker. It crosses over 546 kilometers of continuous permafrost. Now, standard ground engineering assumes you have a stable foundation, right? But permafrost is incredibly sensitive to temperature. If you just go and lay tracks down, the artificial disturbance of the construction plus the solar heat causes that permafrost to degrade. This leads to frost heaving when it gets cold and thaw collapse when it warms up. And let me tell you, thaw collapse is devastating. The tracks don't just bend, they literally sink into the earth. We're talking about billions of dollars of investment just getting swallowed up. So how did they fix it? Section 4. Crushed stone embankments.
So, how exactly do you stabilize a heavy track on frozen ground that desperately wants to melt? Well, much of the railway's embankments are protected by layers of coarse, angular, crushed stone. You can kind of think of this embankment like a giant, breathable sunshade, or maybe a thermos. Instead of trapping the heat, the gaps between all these stones allow for powerful convection. So, cold winter air sinks into the foundation, sort of like ice cubes in a cooler, and actively pushes the freezing line higher, keeping the permafrost safely frozen right beneath those heavy trains. It's this beautifully passive yet incredibly effective shield. Next up, Section 5, heat pipe systems. But look, in some of the warmer permafrost regions, a passive shield just isn't going to cut it. So engineers deploy active refrigeration using heat pipe systems. This uses evaporative cooling, which honestly operates a whole lot like the refrigerator in your kitchen. Step 1, the bottom of the pipe, which is buried deep in the permafrost, absorbs the ground's heat. Step 2, this heat causes a special liquid coolant inside to boil and turn into a gas. Step 3, that warm gas naturally rises above ground where it dissipates the heat into the freezing ambient air. And finally, the gas condenses back into a liquid, drops back down, and the whole cycle just repeats itself. And what's truly astonishing here, this is a zero electricity solution. These massive refrigeration systems work purely on natural thermodynamics. No power grid required. These vertical pipes line the track like little metal sentinels. They are constantly, silently just pulling thermal energy out of the earth and venting it right into the sky. It's just a brilliant, brilliant way to actively freeze the ground and stabilize the massive railway sitting above it. Which brings us to our final part, Section 6, securing long-term stability. Now, the theory is amazing, sure, but dealing with millions of tons of freight demands actual results. And the early data for the specific track section, K123, actually showed a frankly terrifying drop. That cumulative deformation means the track was settling, it was sinking. But then, as the crushed stones and the heat pipes really start to do their work, the data shows the line abruptly flattens out. The sinking stops entirely. This directly proves that these combined active methods practically and safely stabilize the ground over the long haul. But make no mistake, this is an ongoing battle. Nature is pretty relentless. The engineers did just build this thing and walk away. It's a permanent, ongoing war against the sun and water. Early monitoring caught some embankment cracks, right? So engineers had to step in with active maintenance. They laid down these flat sliced stones on slopes to further control the temperature. They constructed earth berms to block surface water from pooling up and melting the permafrost. They even went in and installed extra heat pipes, specifically on the sunnier, warmer sides of the slopes. It literally requires constant vigilance to keep the melting mountain at bay. And all of this brings us to a really profound realization. We started today by looking at how global economic demands literally force us into these extreme environments. But by solving the impossible in Tibet using crushed stone, convection, and phase-changing heat pipes, engineers didn't just build a cool railway. They proved that we can artificially stabilize melting ground. So as global temperatures continue to rise and permanently frozen ground all around the world begins to thaw out, are these ingenious cooling techniques the blueprint for saving our infrastructure worldwide? Something to think about, for sure. Thanks for joining me on this explainer, and I'll see you next time.